Again, just a little bit about myself. I work for a private laboratory or commercial laboratory in California, in Southern California, and we do priority pollutants, EPA methods, 600 series, 8,000 series, etc. But one thing that I get the opportunity to do is develop new methods for clients that have new challenges that it may not be a regulatory requirement, but they're not equipped to deal with these solutions. So we get a little bit of flexibility when it comes to developing new methods for some other contaminants. And so I'm going to discuss a little bit about those. So just as a sort of outline of what I'm going to look at, previous methodology, which probably most of you are already familiar with, so I'll kind of glance over that. And then what I mean by online-SPE, just so the terminology is, we're talking the same language. And I'll talk a little bit about optimizing online-SPE and then some applications that we've developed for some contaminants. I won't go over all of them, but some of the recent ones that we've done. And then also on the mass spec side, we use triple quad, so it's not high-res accurate mass, but just getting the most out of the triple quad through the various parameters and things like that. So as most of you guys are familiar with, EPA 1694, that was a general method for personal care products, pharmaceuticals. It had various different eluent conditions for different classes of compounds. And basically for a commercial lab, this is sort of the enemy is, we don't like to run things multiple ways. We like to find, sort of the Lord of the Rings, one method to rule them all kind of thing. So if you can see Star Wars, the reason for many of these conditions, I believe, is, like it says, these are not the analytes you're looking for. That's a little Star Wars for you guys. Some of the newer developments, these are some obvious things. There's been some research on certain eluent systems that improve electrospray ionization, considering that there's some problems with ionization for different compounds, different classes. And recently we've had more SPE sorbents that have been developed, particularly the polymeric classes of sorbents. And I'm going to discuss one application for a polymeric mixed mode wax one. And of course, online-SPE, I have one sense, it says decreasing analysis time, but as you think about that, you think about the time and labor of sample prep, you think about the electricity, the solvents, the consumables, all of that adds up. And sometimes it's necessary, but sometimes, if we have cleaner matrices like we're used to dealing with, relatively clean, we can pretty much bypass that prep and just go to an online-SPE type of approach. Of course, we have new analytes that are coming out as, as somebody mentioned, I appreciated that we call them emerging contaminants, but they've been emerging, so it's about time we call them emergent. So, and of course, there's been some improvements on sample preservation and collection for broader classes of compounds. And actually, one thing to note is that there's one EPA method, although it's not really being used that much, it's been recently released. It's actually an online-SPE method for drinking water for a specific class of pesticides. So it has some sort of application in the official, accepted, like this is a way to do some things. And then, of course, improvements in instrumentation. We've been hearing about that all day and actually all week. So when I talk about online-SPE, just basically talking about that all the solid phase extraction is done at the instrument. And so that basically means that we can take a sample, we can either load it unfiltered or we can load it filtered, as long as we produce some study that shows that our analytes are not being absorbed or lost. We call it online-SPE, but that's just a fancy way of saying that we have a specialized LC column on the front end. Usually they're very short, like 20 millimeter with a large particle size. And we can load large aqueous samples, like 2 to 10 mils, but usually we're right in about the 5 mil range. And so we like to load the sample at higher flows so that we're not waiting 10 minutes to load the sample. And then elution is done by back flushing that sorbent. And just as a quick point, for specialized matrices, there is something called turbulent flow. I'm not going to be discussing that. And Thermo has a system for that. I've seen it been applied for biological matrices like blood and urine. So the system that we use is actually on the left, but there is a newer system, the ECON Mac system, and we got the system back in late 2010, and we've just been sort of playing around with it and using it for different classes of analysis. So optimizing online-SPE, this is sort of some things that we've looked at. Of course, we load the water onto the sorbent. Whoops. And we've noticed a drastic improvement of washing that SPE. We used to not wash it, and we basically wash it with nanopure water to get off a couple things. One is if there's preservative, as well as if there's matrix salts like chloride, sulfate, things like that. One thing that we've looked at too, we've kind of gotten away from it now because it just sort of covers up an issue, but that's elute, what we call elute focus. And that's basically, sometimes the analytes are sticking so strongly onto the sorbent, it's very difficult to get it off. And so when we back flush, we would sort of spike up the organic to try to get that off of the sorbent. But that's just sort of, we've gotten away from that because it's a little bit bad chemistry as far as trying to match what's going on. Of course, with PFC analysis, there's issues with background contamination, and I've spent weeks on this trying to figure out where it actually comes from, because I didn't just want to change out everything with a kit, and it seems like it's coming from, I think one that had some person that mentioned the degasser, which I hadn't thought of. And so we've tried changing out lines and things like that, but and we tend to use short analytical columns because there's sort of a retention effect when you're doing online-SPE. The analytes go in and then they have to back flush until they come out, and so they've already encountered some retention, so to speak, and sort of time. So we can use shorter columns, and generally 50 millimeters good. And we like fast gradients because we like to elute the analytes off. It seems like a better approach. It seems like faster gradients work well. So this is just a sort of give you an idea of what compound classes that we do. Of course, we don't do the full suite of everything. We don't do all hormones, all organoflame, but we sort of do some targeted and contaminants that have been shown to appear, and so there's a list of about 20 contaminants covering these classes. With the exception of perfluorinated compounds, we do the suite of like 24 compounds, and we also do sucralose by online-SPE, which is very difficult to trap, as well as iopromide. And also pyrethroids, which we do, I think, a standard analysis is just the 8 standard pyrethroids. So this is just an idea of the chromatography that you get. There's, it's not perfect. I tried to pick something that was not when it was new at online-SPE, new column. I tried to pick something that was reasonable that we've done sort of recently. One thing you'll notice, acetaminophen, it's very difficult to get a nice sharp peak, as well as caffeine, we think, because it's zwitterionic. And I think that's it for this one, so it's just a chromatogram. And one thing that we've developed recently was how to trap iopromide and sucralose, because before we had to do multiple injections, similar to 1694 where you had to do different LUN conditions. We had to do just a direct inject and then online-SPE. We don't have to do that anymore using polymeric Strata X SPE, but I've seen in literature that you could use thermo hypercep. Hypercep retained PEP has been shown to extract sucralose. The preservation, this is just sort of an overview of the analysis conditions. I'm not going to go over everything. I just sort of put it in there as far as for your reference in the future. But one thing I want to point out is as far as the mass spec conditions, you'll notice some odd parameters, particularly like CID pressure and the Q1 full width half maximum. I'm going to go into a little bit detail about the latter, but one thing we like to do is optimize transitions at a lower CID pressure, especially when some collision energies, optimal collision energies, are around 10 or 8. It's an indication that potentially the optimal collision energy is even lower, and we've seen that where we lower the collision energy and actually we see that that optimal collision energy actually increase, so it requires usually about 2 or 3 more EV to get that optimal with the lower CID pressure. And then quantitation is strict isotope dilution. This is an example of our PFC analysis. So this is just C4 to C14 PFC, that's just the carboxylates. And so you can see that we actually, one of the hardest ones to do is the PFBA. We're going to present actually at the National Environmental Monitoring Conference in DC, more validation information as far as reporting limits and limit of quantitation, things like that. I'm just giving you a broad view of this analysis just so you can see that it could be done. But we're going to specifically talk about PFBA in that presentation. So with current 537 analysis that we're doing, we noticed that PFBA, we were getting around 5% recovery when we would spike and just using the cartridge that's specified in that method. So this, of course, is with a mixed mode weak anion exchange sorbent. This is just the sulfonic acids, so C4 to C10. And real quickly, just some of the others, the fluorotelmer sulfonates and the phosphas. Okay, this is just sort of a rundown of the conditions. So we tried it with preserved for drinking water, so it's basically 5 grams per liter trisma. So as I was mentioning, the wash step at the beginning is critical. It actually turns out that the trisma improves extraction efficiency in the water. So when we were first starting, we were doing nanopure, and we said, oh, this looks pretty good. Okay, let's try preservative, and we were expecting some losses and things like that. But it turns out that it actually made the recoveries a little bit more robust. One thing that's critical for this, because we're using weak anion exchange, we have to use a high base to elute the analytes off of the SPE sorbent. But as most of you know, not many columns really like to work with high base. So the LC column that we use is it's a Phenomenex C18 Evo column that's stable at high pH. And again, similar CID pressure and the Q1 full width half maximum. And this method is done with, it's not strict isotope dilution, but it's basically isotopically labeled analytes or isotopologues for the certain classes, so the carboxylates and the sulfonates and things like that. So one thing with matrix issues, I just want to talk a little bit about that, is that we've had some samples where we've seen very high chloride, and this is sort of the biggest enemy of internal standard suppression for us, and especially for this type of method. Originally, we had validated our method for pyrethroids for only maybe a few hundred ppm of chloride and sulfate. But we have started been getting samples that's just not reasonable. We've been seeing higher chloride and higher sulfate. And so one thing that we've looked at that seems pretty promising is using these Dionex On Guard cartridges. Is basically we take a sample and pass it through these cartridges. You can actually see on this one the change in color in the middle portion, which is the silver, pulling out high amounts of chloride. We've seen about a 90% reduction. So that sample went from 2,000 ppm chloride to about 200, which is in the range of where we sort of validated our method. Briefly, filtering. We've looked at filtering because we used to just not filter across the board, but it became apparent that we really needed to filter because sometimes you get that one rogue sample that has particulate and that wreaks havoc. And so we're starting to look a little bit more closely at filtration. And but with particular classes like PFCs, this can be an issue because the higher molecular weight acids absorb to certain materials. So, but we've seen that with glass fiber filters that it works pretty well. Just as an illustration of what we've done to sort of minimize matrix effects, just using mass spec to do this, is we had an issue with, we were running hormones for EPA method 539, and we were seeing some low-level testosterone and androstenedione hits in finished drinking water. And if you know that method, it's not a very good method. It's really screening method. There's one transition that you're monitoring. And so the question became, well, is this really testosterone at 0.1 ppt or not? And so we started looking at, well, what can the mass spec help us to try to tell us if this is truly a hit or not. And so I started looking at the effect of the full width half maximum because most applications that we see, they set it at unit resolution at 0.7, and that's how most people just set up their methods. However, this is a case of one of the pyrethroid cyfluthrine. You can see two different transitions, one on the top and the bottom. And then you could see that the top is the total and the bottom two are just the single transitions. And you could see that there's different noise coming from different transitions. And so as we lower that full width half maximum, you'll start to see that noise starts to decrease. And then on the side here, I've shown sort of the expanded peak without any smoothing, so you can get an idea of the full data. And so going lower at 0.2, you can start to see that the little hairs of grass at the bottom starts to diminish. And so this effect, and this is at 0.04 Daltons, but you notice that the response is now completely, quashed. There's sort of a diminishing return. And this, of course, it has to do with mass stability because we're targeting a particular transition, and our mass calibration in reality is drifting in and out a little bit. So this is sort of a plot of sensitivity versus full width half maximum. What I should have plotted, and I thought about later, was signal to noise to full width half maximum, so you could see sort of there's a maximum at which you can lower the full width half maximum, but I didn't think about that actually till a couple days ago. So, but that would have been a better way to present this chart. So we've liked to go into the 0.2, 0.3 range because it's a decent trade-off. We lose a little bit of sensitivity while gaining signal to noise. Some things about special things about how we do mass calibration. This is the fourth point down in the bottom. We use the phosphoric acid clusters in both positive and negative mode, and we use 9 mass cal points now. We find that because we want to go to a lower full width half maximum, we can get mass calibration even on a triple quad that can last longer. Whereas before we used to only mass calibrate maybe once a year, if that. just for unit resolution type of work. The second point mentions that the mass stability in the specification for the TSQ series is around 0.05 Daltons. And this is actually, we verified this. It's actually on our system that we've looked at it. It's even a little bit better, but I understand that this is sort of an average and they don't want to overstate it, but definitely 0.05 is, and it's decent for triple quad work. This is just a graph kind of illustrating. We've done some data acquisition in profile mode because we've seen that with the centroiding, it doesn't always produce, it doesn't always centroid correctly. So we've done some work where we've actually collected profile mass spec data just so we can see what's going on with the mass spec data on a continuous basis on the mass peaks. But just to illustrate, the red bars are sort of the mass stability. So you can see when you're operating at 0.7 that there's no issue. The masses, the true masses will be within that window and you won't have any issues. But as you, like this is a 0.06 Dalton full width half maximum, you could see that now the peak is sort of outside the mass stability. And I don't know if I really represented this correctly, but what I was trying to get at was that as you lower the full width half maximum, that your actual peak of what you're seeing is sort of a moving target, and that's ultimately the root problem. This is just showing that after mass calibration, you can actually, I'm sorry, let's see. Yeah, so the red is before mass calibration. This is 3 ions of a phosphoric acid cluster, clusters, yeah. And you could see that the green bars for the 3 masses, they're still pretty high error on the low full width half maximum, but once you get down to 0.2, 0.3, 0.4, 0.5, it's pretty much, it's all less than 50 ppm. So you might think, well, you're not doing high-res work, why do you care about this? Well, it's because we're lowering our full width half maximum so that we could discriminate from matrix background. One thing as far as online-SPE for data applicability that's worthwhile to note is whether or not we're measuring bioavailable contaminants. This has come up with our pyrethroid method because pyrethroids are very lipophilic, and if there's suspended particles in the sample, for example, if it's stormwater that has this type of matrix, that whether or not we're actually measuring bioavailable contaminant, because that has some indications on toxicity and things like that. So personally, I don't know either way, but all I can say is this is how we do it. And but there's 2 theories that particles, even if you don't filter the sample, particles could be trapped in the media, and in that case, the particles would be solvent rinsed with the elution during elution with the mobile phase, which includes a high gradient of methanol, or at turbulent flow or high flows when you're loading the sample, those particles could actually pass through if they're small enough. And so at that point, your analytes would go along with the particles. And so this is something we haven't really looked at because we're a commercial lab. We don't have all the time in the world to research this, but it would be something of interest. So pretty much any analyte with high KOEC might be trapped in suspended solids, so it's just a concern. And this could possibly include PFCs, especially the longer chain PFCs. So just some final thoughts. From my point of view, most analytes can be done by online-SPE, although I would add to the exceptions things like dioxins, and we're talking about electrospray, LCMS, that side, just to try to get rid of the prep. If it's possible to get rid of the prep, then that's what we want to do. And so if we have a clean matrix like drinking water, or relatively clean like even storm water, and we can just bypass the prep and make it faster while not sacrificing the quality and trying to assess the quality that's the sort of approach that we want to go. So online-SPE, it can be a sensitive technique because we're loading 5 mils of water sample with an offline extraction, and most of the standard ways of doing things. Most of the extract is actually wasted, if you think about it, because you extract down to, say, 1 mil or half a mil or quarter mil, and how many microliters are you going to inject? Maybe a fraction of that. And so with this method, you take 5 mils whole water, it's basically ultimately going through the mass spec. One thing that we're looking at now is to adapt this to soil analysis if an aqueous extraction is used. I don't want to assert too much about this, but one approach could be to do an aqueous extraction of soil and take that aqueous extract, even if it's methanol, in the case of PFCs, because our sorbent is weak anion exchange, it offers the advantage of, at least the claim is 100% organic wash conditions. So we've seen that we could do about 10%. So if the extract had 10%, then this could actually be loaded on the sorbent without adverse effects to recovery for shorter chain like PFBA analytes. So with that, I'll take any questions if there's any.
Thanks, David. Any questions?
On your online-SPE for VAX, weak anion exchange, have you noticed that the shelf life is not as long, or let's say if you use HLB or C18?
So we've tried we haven't tried HLB with the PFCs. We tried HLB a long time ago when we were trying to do sucralose and isopromide. We went away from that. We sort of stuck with the Hypersil, the Thermo C18. One thing I should add is that, and I didn't mention, is that we stack cartridges. So we actually have a C18, Hypersil C18, and on the back end of that is the Strata X. So the sample actually loads in the C18. We get all the normal trap on C18, and then those that break through, like isopromide and sucralose, we trap on that polymeric sorbent. But with the wax, we haven't been doing it long enough to notice any shelf life with the online-SPE method.